so I thank the organizers for giving me this opportunity to present our work here. I will tell you something interesting about interacting fields at spatial infinity. So this work is based on these two papers. One is by Alok, Shridhar, Shufrat and Pushkal, and another is like ongoing work with my collaborator Anupam, Athira, who is in audience, and Shufrat. And so let me first motivate you about the problem. So what is spatial infinity? So we take our usual like 3 plus 1 dimensional flat space, and we take this radius coordinate, the r, to the infinity, keeping all the other coordinates fixed. Then we get the spatial infinity. Let me show you what does it mean in the Penrose diagram. As the previous speaker was already talking about the Penrose diagram. So he was talking in black holes background, but it is just empty flat space. So there is just some light cone here. So these light rays are going to this like in 45-degree angle. They're this going to sky plus. And then there's some massive particle which comes from like very like past time like infinity, so I minus to I plus. And there are some regions which is like very much like space like separated from this light cone origin, and which is like I0, where we can reach if we take r tends to infinity. So what we want to study, like we want to study this massive scalar fields at spatial infinity at near I0. So it might be like you might be puzzled, like why we are studying this massive fields does not go there at all. So why we are doing this thing? It's okay, maybe there can be some exponential fall off of that massive field near I0. So why that is interesting at all? Okay, let me tell you why it is interesting. This is interesting because of the holography. What is holography? So, okay, I am using in a weaker sense, we are using holography of information. What does it say? It says if we take a constant time slice, a Cauchy slice, the information about the bulk of the Cauchy slice is already available near its boundary. And it was, this statement was like established by Raju and his collaborators in a series of papers. And it is already established in flat space for massless field when it is coupled to gravity, and in ADS. So it is a statement about gravity. But so in natural question will be, so I was saying like in flat space it was only proved for massless fields. So natural question will be, what happened if we include massive field? So can we just generalize this principle of holography of information, like you have the information about your bulk, like Cauchy slice in the boundary, when massive field is coupled with gravity. So this is this Cauchy slice, this constant time slice here. And so a natural boundary of this Cauchy slice is this I0, where we can reach with taking r tends to infinity. So before going to doing any gravity calculation, like talking about quantum gravity, let's take a simple problem. Let's study some non-gravitational field theory in Minkowski space for massive fields near this boundary of the Cauchy surface, which is I0. So from the next slides, I will not talk about any gravity or any holography. It was just for the motivation of my talk. Okay, so let me talk about the setup, what I will be using. So I will just take some slicings of the Minkowski space, which are often called de Sitter slicings. So there is this time coordinate in flat space t, and there is this r, which is this radius. And we can take t goes to rho cos h tau and r goes to some rho sin h tau. And this coordinate patch, they actually like fill this space-like region of the light cone here. So if you see this, this vertical, this dashed black line, these are like constant rho slices, and these are like each of them is some de Sitter 3 slices. So it is less like in general we decompose in terms of sphere coordinate. Now we are decomposing in terms of de Sitter 3 coordinates. Nothing more than that. So now here our coordinate is some rho and tau and omega, and we can combine tau and omega with some capital X, which is some de Sitter 3 coordinate. And okay, this is some notation. Just I am writing some X, this de Sitter 3 coordinates in terms of tau and omega. And now what we can do, we take this, I was telling, these vertical lines, these dashed lines, these are like constant de Sitter 3 slices, these are like constant rho slices, and each of them are some de Sitter 3. So if I take some rho tends to infinity limit and then rescale the metric, we get something very close to I0. I0 is here, this point, but here we are getting some blow up of I0, which we will call I hat 0. So like we often call it a blowing up of spatial infinity. But actually, we can go from I hat 0 to I0. So, see this yellow line or the orange line here is some. If you take some finite time slice, finite region, like finite time region here, and then if you squeeze them, like take rho tends to infinity, it really goes to this this I0 point. But the point is, we will see we cannot take this finite time region. We will see, like we actually are not going to I0, but from now on we will be only talking about I hat 0. There is some dynamics going on in I hat 0, some interesting thing going on. We'll see. So now we follow the same Peskin level QFT, like we have some scalar field, we have some equation of motion, but the coordinates are different, and we solve the equation of motion, we got the solution. And here, like in terms of earlier, in terms of, we had some in terms of spherical harmonics, now we have in some digital 3 fields. It's not quite important, but look at this radial behavior. It is some k I nu m rho by rho. It is some Bessel K function. And what is this Bessel K function? How does it behave when rho tends to infinity? It falls off like exponential of minus m rho. That was this exponential fall off I was saying in the beginning. Like these massive fields, they go from I minus to I plus, but they might have some exponential fall off near rho tends to infinity. So what we can do, we can just strip off this exponential factor and take the coefficient of the scalar field. And we can define some extrapolated field. So there is some exponential fall off, it is falling down. We can just take some e to the power of m rho and multiply with the field and define some extrapolated field, which is Zx. This is some extrapolated field we are defining. Now, can I do a field theory with this Zx? That's the question. Can I study some field theory with this Zx? Okay, this paper with Alok, Shubhrot, Pushkal and others people, they actually studied this 2-point function with this field. And they studied, okay, this is actually when you study the 2-point function, it's not sure, like it's not always true, like it fall off like e to the power minus 2 m rho, because each of them is going like e to the power m rho, like one is going e to the power m rho and another is also going e to the power m rho. So the total thing goes as like e to the power minus 2 m rho, but it's not always true. But they actually solved this problem by smearing the extrapolate field with some good smearing function Gx. And the smeared 2-point function they studied, and it is really well defined. And because it is actually the 2-point function of this Zx is some distribution. It has some Dirac delta like properties. That's why just Dirac delta is only defined under some smearing. That's what they got here. And now they also like decompose this smearing function in terms of some YLM, like some spherical harmonics, and they found some nice properties like this tau dependence is actually analytic in some domain, in some imaginary time domain, like minus pi by 2 to plus pi by 2. And as you know, some analytic function should always have support over all real tau. That's why we have to integrate over all tau. Okay, it's not like we cannot just focus on some compact region in tau. So this is some free field construction. We did not enter the interacting fields yet. And with this, so this I hat 0 is this purple line here. It is the full line, and we have to like smear over the full line, not over any small compact region. And that's what the field here in the full line, they are causally connected with the bulk. So you can do some bulk reconstruction thing, like you have some field here in the bulk, and you can construct it with this some jet, and we have constructed this as this kernel here. With this S is some kernel. So Z is some boundary field living in this I hat 0, and you have some kernel, and with you integrate it, you get some bulk field. Up to this, it is some free field construction. But the real question is, can you construct some interacting field theory with this Zx? Let's study. Okay, so now we'll change a language a bit more. So as we are smearing over this x coordinate with some analytic function, and this the time in the usual interacting QFT, we studied time ordered correlation function. But the time ordered correlation function is some theta function, and that does not respect this analyticity property. So the time ordered endpoint function, they are not very good thing to study in this scenario. We can choose some other things, which are the Weidman functions. So what are Weidman functions? There is no time ordering apparently, and this is just some operator ordering here. So I just give you some operator like phi x1 dot phi xn, and I say okay, just compute it. But there is some inherent, like there is some hidden time ordering in imaginary time. So the real time has no ordering, but we order the imaginary time epsilon 1, epsilon 2 in a particular way. And actually we can visualize this ordering here in some like nice like contours. So because there is some, so this real part is going from minus infinity to infinity here, from right to left, and imaginary part is going from like from the bottom to top, and so they have different imaginary components. So we cannot place them in one line. We have to place them in different line, and so these lines, this like time evolution lines, they goes like zigzag this like way. And so this is some generalized some OTOC contours or Swinger-Kelly's contours, and everything is same if you just replace the time ordering symbol of Peskin and Schroeder with this contour ordering symbol. And then you get some extra, there is some extra thing, extra baggages, there is some extra rule for the propagators, extra rule for the vertex factors that I will just show you. So now because you have different contours, so you have to specify them, like how you are connecting these propagators. So there are different prescription of these like propagators. So if like there can be some time-like propagator, and like some anti-time ordered propagator, then some Weidmann propagator, anti-Weidmann, these kind of things will happen. So these are some general rules. This is some already well-studied theory, Weidmann functions in quantum field theory. But we need that to study the special infinity fields. Okay, so first we face this problem. We face like this wx1.xn does not have a good falloff. Like what do you mean like good falloff? Like if you remember in our extrapolated dictionary, we define this as e to the power minus m rho. But now I find if you take only, say, if you take this point and you just like do some manipulation, you find it has supported for all e to the power a. Yeah, how many minutes? Sorry, 12 minutes. Yeah, give me 2 more minutes. I will just finish. I am just ending. Yeah, 2 more minutes. I will just end. Okay. So so there is this e to the power a, and a can be anything. So this does not respect the dictionary we defined. So what you are finding, even after smearing with some analytic functions, the interacting correlators do not die off with the right falloff to obtain the extrapolate correlators. So what do we do? How to solve this problem? Okay, we have a proposal. We are saying like if like first go to this momentum space and extract out the coefficient which is like the on-shell coefficient. Like this, like all the delta functions are multiplied with this, and you extract out this coefficient. And if you do a field theory with this coefficient, that really does have right fall of e to the power minus m rho. And then we can write the special infinity fields with just like this, like we can also write these correlators in terms of the single operator. We can just, for a single operator, we can just extract the on-shell part, and we can write the special infinity fields in terms of this on-shell part. And then if you remember, I just showed you in the Weidmann functions, there are time or like this usual like the Feynman like propagator, like time ordered propagator. They are not really on shell, but here we are putting everything on shell, so that in the time ordered propagator you should only take extract out the delta function part, not the part this PV part. So these we have some new Feynman rules, and with the new Feynman rules we can calculate some correlation function at I hat 0. And there is a nice relation that we found. Like this relation is like this. These are some asymptotic fields here, and these asymptotic fields are related with this like asymptotic fields at I plus and I minus in a nice way. They are just superposition of this fields at I plus and fields at I minus. And with fields at I plus and I minus, they are free. But as these fields, they are superposition, so they are not the free algebra. And I will just take 1 more minute. I'll just give you one example how all the things are fitting in. So you have two ways to compute this thing. One is you just put the propagators on shell, and other is you write everything in terms of the algebra. So in terms of the algebra, we found the 4-point function is only real. And here we have computed many diagrams with our new rules, and we found the contact diagram is 0, exchange is 0, but the loop is non-zero. But how these two things are fitting in? Okay, let me show you this contact diagram. It is always some I lambda. There is no real part. That's why we are getting it 0. Exchange diagram, if we like cut this propagator and put it on shell, then we can have some real part. But the point is, because of some kinematic concept of the phi cube theory, we can never have this real part. Like we can never put this thing on shell. So that is it is 0. But this can be done in loops. That's why the loops are non-zero. And similarly, you can calculate some more general function for in between I plus, I minus, and I0. I am not going into that. So here is my outlook. Like can we find can we recover S matrix from these new observables? Can we generalize this thing to with when coupling to gravity? Like can we really find holography? Can we find some relation with celestial CFT? These people are talking about for a long time. Can I find some relation with them? So that's it. Thank you for your patience and giving me some extra minutes. Thank you.